Next, we have Jean-Marc Petit, who's going to be telling us all about OSSOS, which was a very high-impact large program.
Good morning, good afternoon, good night, everybody. First of all, in case I don't make it to the end of my talk, I want to thank the people at CFHT. I mean, you have a very good telescope in a magnificent site, but a fantastic team which took all those observations and allowed us to do this science. So thanks a lot. Where is this? So the OSSOS actually is the last part of a set of survey that started from with CFHT. So we have a whole slew of smaller and bigger surveys. So we have CFHT, which is CFEPS, and then we have the high latitude part of it, and then Petit knows it's a smaller kind of OSSOS survey, and finally the OSSOS by itself. I wanted to show you this plot that you've seen from Wes 2 days ago, because OSSOS stands out here because this is the only survey where we have a very good orbits for all the objects that we characterize. So we have a full sample and we follow them all, and that's why it's the circle is full. And that's what allows us to do all of the science we've been doing with that. Okay, so we have this sample of objects that were detected in all those surveys. So over 1,300 detections and 1,146 characterized objects, and only 35 were not tracked. So on the top right plot, you see the kind of distribution that you get after just 1 year of observation. You have heliocentric distance, inclination, that's very easy to find. But then you have to track things for a longer time, for a few years, to get orbit clarification. And you get the plot at the bottom where you have semi-major axis versus inclination, and you can see that it's no longer all pile of things. It's structured, and with a lot of structures. So you can see on the left a lot of the number of objects in different classes, which actually come from this kind of classification paper by Gladman et al. So you have the semi-major axis on the bottom and the eccentricity on the left. And essentially, we're interested in all the objects between the two vertical dashed lines. So we have the classical object in the middle, you have all the resonances at very specific distances, and you have below this sketchy line, you have everything which is stable essentially, and above that you have essentially everything that is unstable when it's not in the resonance. And it's all based on the current day dynamics of the objects. So all the thing that we've seen before is a set of objects. Okay, here I'm missing one. So these are the objects that we found. So they are here put into on the right. You see them in resonant objects in blue, detached objects in orange, green are for the scattering ones, so the unstable ones, and you have the classical bed, which is the small box in the middle of all of that, which I expand on the left. And here the color coding is different. It relates to the inclination of the objects. So, and you can see that the blue, low inclination, orange, medium inclination, and green, high inclination objects tend to have a different dispersion in the AQ, Q being the pericenter distance, in semi-major axis pericenter distance plot. So they tend to be in different places, even though they overlap. So, but this is the view that we have, which is a biased view of the solar system. And what we want to do is to create a model that will provide a set of orbit that correctly reproduces the observed sample. The thing is that this model is then used to plan future campaign, provide support for analysis of all the data set, and that highlights something new in discovery. So the model that the draft version of the model have already been given to some people, and it has been used for several things that I will show you later. And all of that comes from the desire to have a picture of the orbital population that is consistent with the current state of knowledge. How do we do the modeling? So we take either parametric models. That means that for each distribution, inclination, semi-major axis, whatever, you take arbitrary functions and you put some parameters in them, or you can do the debiasing of the data. That's another thing. Or you can do some dynamical modeling based on some kind of uniform distribution which get eroded to today and whatever. So all of these, you can do that each separately, or you can mix them all, and that's what we're going to do. So for example, for the main classical belt, we have here, if you look at the structure of in the semi-matrices pericenter distance plot, you see that there is a lot of structure in here, and we could not find a parametric representation of this. So this is done by debiasing the HU distribution. But in the same model with the inclination distribution, the side distribution, and the angle, the positional angle distribution for the orbits are all parametric. Okay, and we will play with that, and we see whether we can actually get a model that reproduces the observation. So here you see the distributions on the top right, absolute magnitude, bottom center, the distance of detection, and on the left, the inclination of the objects with respect to the ecliptic. And you can see that the dotted lines are the interesting functions, interesting distributions, and the solid lines which overlap with the dotted red lines, it's difficult to tell them apart, because the dotted red line is the detection, the real detections, while the solid line is the actual debiasing of the bias model. Sorry, not debiaser. We can do the same thing with the resonances. Here is the 2-to-1 resonance. What is interesting in the resonance is that they come close to the sun, or closer to the sun, at specific direction with respect to Neptune, and so that requires some very specific kind of modeling. And here we can do that only with some dynamical modeling. And for that particular resonance, we have this potential binodal inclination distribution, which looks like the one we have also for the main belt, but not for the other resonances. We have more resonances that we've been able to probe with OSSOS, and in all cases of the resonances, you see that it's very important to know exactly where you pointed and your efficiency in different directions, because you tend to see more or less objects depending on where you're looking with respect to Neptune. One thing that we were able to do is with that kind of sample is that we confirm somehow that the gravitational streaming instability is a viable way of creating an object, as mentioned by Wes the other day. This is good to explain the binaries, and here we're just looking at the size distribution of objects. So on the left you see some simulations of the formation of the streaming instability and gravitational collapse. And these kind of simulations tend to create some size distribution of objects which are well matched by our detections. So on the right you see the detection, the size distribution, distribution of absolute magnitude, which is a proxy for the size distribution of our object detected in OSSOS, and we match the kind of shape that were proposed by the people doing the streaming instability. So that's probably something correct. From these population estimate, these models, we can do some population estimates, and here we have population estimate at a specific value of the absolute magnitude, and essentially what we see that all different populations tend to be equally populated. So, and what is interesting is that even going at large distances, the resonances are very well populated. And the 522 is as populated as the Petit node with 322, which is while the 522 are much further out. So it's kind of interesting to see that there are so many objects even at the large distances. Here we set the population at a specific H value of absolute magnitude, which is roughly 100 kilometers, but it depends on the albedo, and the albedo is at different values depending on the population and on the individual objects. For example, the canonical value is 5%, for the cold bed it's 15%, so this value of H corresponds to 60 kilometers. For the hot bed it's slightly less, so it's 8%, so corresponds to a value of 80 kilometers. And our course, this object that we visited, is very bright. It has an albedo of 0.24, so 24%. So it would correspond to this H of 8.66 would correspond to 50 kilometers. So that's why also we keep it in terms of H, not on anything else. We can do also other things like measuring the number of collisions between different populations. And here on the left, you see the where the collisions occur, and then their speed, position on the horizontal axis, speed on the vertical axis, and the color coding tells you the probability of collisions. And we also were able to show that there is no catastrophic collision in the current Kuiper belt, and we also could match with the cratering records on the Pluto and Chiron that was measured by your horizon. So all in all, OSSOS is a high impact. So we'd had 30 papers, just the ones from the core team, with 950 citations. And yet it's a smallish, large program which is only 40%, 35 to 40% of CFHT. And you can add to that the core OSSOS led by Wes, and who has, with core OSSOS in the title, only 11 papers, but probably more, and more over 350 citations. So the OSSOS model has been used for TNO collisions, cratering rates, catastrophic collisions, post-Holocaust target search, and even DEEP, the other large-scale survey, used our survey to debias their own data. And the model will be available soon, hopefully, on our website.
Questions? Any questions? Are there any questions online? If you were to redo OSSOS, would you have any changes in terms of, was it like the perfect LP, do you think, like in terms of the design and what you ended up getting out of it? Or would there be anything that would be tweaked with hindsight?
Oh, I never thought of that. Well, essentially, we've done OSSOS. Now we know that, so we need to go deeper. So that's classy.
Yeah.
Essentially, what we need to do is classy with a scale of CFHT. Essentially, yeah. I mean, go deep and wide. Right now we're going either wide and shallow, kind of mid-scale, mid depth, or deep, like classy, but we need to go deep and wide. And that's one very nice community survey that could be done.
Sorted. Excellent. That's thanks, Jean-Marc, again.